Okay, welcome back everyone. So in previous videos, we looked at how the compiler is taking some higher level instructions, say C instructions, and what would be equivalent statements in assembly. And we want to do something a little bit different starting in this video. So previously we were looking at kind of this step here, right? You have some code in a language such as C, and we're looking at how going through the compiler and getting this code to be an assembly language. And there's another step in the process before we have it in something that the computer can truly understand, before your processor can truly understand. Because the computers don't think in assembly language, they think in machine language instructions, right? Part of the instruction set for that processor, which is all in binary ones and zeros, okay? So what we want to do, and we're going to do that, we're going to look at some of these kind of regular type or RType instructions and how they go from instructions in assembly to something that in ones and zeros in binary. So we're going to look at how we basically encode an instruction into binary. Each instruction in the ARM leg V8 instruction set is 32 bits. Okay, so we've got one word, 32 bits for each instruction. Okay, and really, when we look at assembly, it's typically, for the most part, each line is a unique instruction. Okay, so we'll do it one instruction at a time. So let's start with this add instruction here. Okay, so we've got add. We're going to add the value of value of x1 and x2 registers, and we're going to store the result in register 0. Okay, now the first step of this process is to determine what type of instruction this is, right? There's different categories for different instructions, and I'm going to strongly encourage you to get used to looking at this sheet here. This is the instruction set for the ARM leg V8 instruction set, okay? The core instruction set, right? And there's a ton of information that's that doesn't make sense to memorize. You're not expected to. There's no need for it. But you need to get used to being able to understand how to look up and find the information that you need. Okay, there's an awful lot of relevant information in this reference sheet. Okay, so one of the first things that we're going to do is we want to take a look at, we want to find the add instruction. The goal is to convert this to binary, right? This instruction to binary. And one of the first things we want to do is we want to find that add instruction, which in this case is the very, very first one in the very first instruction listed. And look here where it says the format. Look for where it says the format. And the format is listed as R. Okay, so this is an RType instruction. Okay. Here's another way to look at it. This is kind of a little bit of a different view. Step 1, right? Find the instruction on the reference sheet and identify the format. Okay. R is our regular instructions. That's what we're going to focus on this video, is looking at those. And what we're going to see is for an RType instruction, one of the reasons we need to know that right up front is we need to know which instruction format we're using. So if you look down here, we could see that we've got RType, IType is for immediate, our data transfer instructions, D, and so on. We've got our branch instructions, we've got some of our conditional branch instructions, and so on. These different instruction types will have a different format. What the format is telling us is all of the instructions are 32 bits, okay? But we're going to break up those bits. We're going to break up the bits for those 32 bits to represent different pieces of information based on the instruction. Okay, we'll see that momentarily, right? So on this, if I'm here on this reference sheet, I can kind of come around on the first page here and kind of let me zoom out a little bit, and we could see here. Here's an example where you're looking at these instruction, the formats, right? And so we're looking here at this RType instruction format. Okay. And so I've got that summarized here on the slide. So this is key. This is critical. This is telling us that we've got this something called the opcode that's bits 31 to 21. We have something called the RM, bits 20 to 16. A shift amount, which we'll talk about later, these 6 bits, 15 through 10, and so on. Okay. All right. So now we know this. We know how we're going to break up the instruction because we know it's an RType instruction. We know how we're going to break it up into these different 5 pieces. Okay. This first one here, the opcode, this is a binary sequence, right? That is telling us encoding what is the instruction, right? Is it an add instruction? Is it a subtract instruction? Is it a logical or and instruction, right? Different things that the processor can compute or do. The opcode is telling us what is the instruction. Okay, what are we asking? What is the operation that we're asking the processor to do? Okay, so that's effectively what's being stored there. So the information that's going to be encoded, we'll look at how we get it into a binary format momentarily, but the information that's going to be included here, okay, in this case is going to say, hey, that opcode is going to indicate that we are adding something. Okay, and we have one destination register and 2 source registers. Okay. Now, one thing that's a little bit strange is you'll kind of see why later on this is the case. The destination register is actually stored here. Okay. Is the last one. It's a different order than how we write them in assembly, right? We're going to actually write that as the one furthest to the right. The destination register is the one that gets the result. There's actually a reason for that. We'll see later on about how it makes some things easier to have a format like that, but it really requires kind of looking at the processor and seeing where some bits are getting mapped to different things. So we'll come back to a later point and say, why does that make sense that it was designed that way? But we're not really there yet. So for now, just kind of keep in mind that that's the case. I'll show you how you can remember it by looking at the documentation in a moment. Okay, and then the RM here is for the first source, and our RT or RN here is for the second source register. Okay, the shift amount we're going to always, for our purposes, we're always going to list it as 0. Okay, you could shift to you could store some information for shifting to indicate like multiplications by power of 2, etc. We'll see some of that later on in the course, but for now, and for anything that we're doing for converting to binary, we're just going to leave that field as zeros. Okay. Now, I want to mention something. I talked about how the destination register here is actually the one that's the furthest to the right in bits. Okay, here's how you can avoid making a mistake where you put it in the wrong order and avoiding kind of having to memorize stuff, but finding the information on your own, which I think is really important, is if you look here in the documentation, take a look at how, when we look at the add instruction, it tells you, it has some information here on the right that shows the operation in Verilog, okay, which is similar to VHDL if you're familiar with VHDL, in that we're looking at how RD is it's the register. RD is the one that's getting the result, right? It's the one that's being written to, right? While we're reading the other 2 values and adding them together. So this is telling you the RD register is the one that's getting the results, right? And then if you go to, then if you look at the format here, RD here should be the one that's being written to, okay? That's a way of being able to look it up and remember that by checking the documentation. Okay. For the opcode, the documentation here is showing us that what the opcode is in this case actually hexadecimal, 458 in hex. Okay, so if we convert right, 458 in hex, if we do that in, if we write that out in a binary, we're going to get this, right, in binary. Okay. Notice that's 12 bits, right? Notice this here is 12 bits. Okay. Notice down here we do not have 12 bits. We actually have 11 bits for the opcode. Okay. It's very easy to accidentally be off by 1 bit here. Okay, because we're going to drop one of these bits. And to remember which one of the ways that you can do this is you can look at the second page of the reference sheet, and you can look here and find the add instruction, right? And look at it and say, well, what is the opcode here? It's going to be dropping one of those bits, and it actually drops the leftmost bit. Okay, so notice this is the same sequence I just wrote. Okay, except the one I wrote converting the hex to binary was 12 bits. We only have room to store 11. We're dropping the leftmost bit. Okay, so just keep that in mind, right? So we know now right? We know that this is the opcode. This is the opcode for that. I can go ahead and just write that right in. Say, okay, let's go ahead and just write that. Okay, are 11 bits. Okay. Now, we're not done, but we're getting close to done. That's one of the harder parts. Now we need to just map the registers, okay, into the appropriate fields. Okay, remember RD goes to the rightmost one, and then we have these other RN and RM. Okay. It's actually going in the reverse order that you would expect. Okay, I think I wrote that the other way up here, so it's important to double check the documentation. Okay, that's a minor point. You actually get the same result in this case if you flipped it around, but unlike the RD one if you didn't, but because we're adding. But anyway, so to fill these in, it's pretty simple. Okay, we have register 0, 1, and 2. 0, okay, 1, and 2. And if we look at this, another part of the reference sheet, it's very easy to see how things map, right? Especially the ARM registers are particularly simple to do this, right? Register 0 through 7 map to numbers 0 through 7. So they actually map the address of the registers to just what the number is. It's very straightforward. So another way, just to kind of make that a little bit more clear, right? So the RD register is register 0. I'm going to come here and say for register 0, it's simply 5 bits that are all zeros. Okay. RN is register 1. Okay. I'm trying to write it so we can convert it to hex very easily. Kind of double check that we have the right number of bits. Okay. The shift is 6 bits are always going to be all zeros. Okay. And RM is register 2. Okay. So this is our final result in binary. Okay, that is the result of taking this add instruction and converting it into a binary. It's binary representation. Okay, so that's actually how this. If you took that assembly language instruction, one thing I want to point out is notice that there's a very clear, right, mapping of an assembly language instruction directly to a 32-bit machine language binary instruction. Okay, it's very easy to go from a assembly language instruction to assembly language. They're not that far of a level of abstraction away from each other. They're very close. Okay, and that's part of the benefit of assembly language, is it's something that is okay, it's an ugly thing to use. It's not always very user-friendly. It can be complicated to write things into it and easy to make mistakes. But it still is human readable, okay? And it's also very easy to assemble it into machine language. So it's very close to machine language without us having to constantly be looking at ones and zeros and figuring out what they are. Okay, it's kind of like the lowest level thing that you could look at and read and program in, as a human that can't just look at thousands or millions of ones and zeros. Okay. And very important for understanding how the hardware works. All right, we'll do more examples. All right, this was an example of an RType instruction. So for other examples that I'll do in recorded videos is we'll do at least one itype instruction, which we'll talk about what those are in another video. We'll also look at a dtype instruction as well. So as we kind of move through the course, we'll look at we'll have some videos, examples on those, and we'll have follow-up exercises that kind of allow us to practice encoding different types of data, different type of instructions. And we'll find that this is really, really important when we go and we actually try to understand how a processor works. One of the first things, right, is to basically say, okay, here's an instruction that's running on the processor. Well, how's it encoded in binary? If we don't know how to do that, you're kind of stuck and you can't really even go to the next step. Okay, so it's a really, really important prerequisite knowledge for things that we're building up to. But we'll follow up on that at a later time.